Okay, so we were talking about here the motion of the airplane. So as we have seen, the airplane is initially at this position. This is position 1. For position 1, the angle here is 60 degrees. And we know the second position, position 2. For position 2, the angle is 15 degrees. And we know that the airplane is starting from rest, so V1, velocity at state 1, equals to 0. And we want to determine what will be the velocity at state 2. Okay? So the velocity at state 2 is unknown. In order to determine V2, we can apply or the work and energy, or here also we can apply conservation of energy. Why we can here apply conservation of energy? Because if we draw the free body diagram of the airplane, we have just the weight, W, and the tension T in the cable. Okay? Now, concerning the weight is a conservative force. Now, for the tension, what will be the work of my tension in this problem? When going from position 1 to position 2, I am moving on a circle, okay? And the tension is along the radius because the tension is along always the cable. So since the tension is along the cable and the cable constitutes the radius of my circle, so the tension is always perpendicular to displacement, okay? Because you know that for a circular path, the tangent line is perpendicular to the radius. So since T is perpendicular to motion, so it cannot produce any work, okay? The work of T is 0. And then all we have to do here is to say that the only force doing work is the weight, and therefore we can apply conservation of mechanical energy between state 1 and state 2. So here I considered that state 1 is called it's state A and state 2 is state B. Then we need to write to replace. The initial kinetic energy is 0 because as we said, it's starting from rest. Now concerning the potential energy, whenever you want to define potential energy, you need a reference line. And here, the best option is to choose this part as a reference line. Why? Because you know the length of your cable. Okay, you know the length of your cable, it's 20 meters. And you know the angle, so you can find the height. So if you project here, if you project the position of A, we have that I am below the datum, and since I am below the datum, it's a negative potential, and the distance is 20 cosine 60. So since this distance is 20 cosine 60, then I can say that my energy, my potential energy is minus mg times 20 cosine 60. Okay? Now, here in their reference, instead of taking this reference, they considered the floor as a reference. If you want to take the floor as a reference, it's also right, but then you will have a positive potential, and your positive potential will be equal to plus mg times this distance, and this distance is the difference between this part, which is 20, because when the cable is at 0 degrees, it will be this height, this should be given in the problem, it should be clearer. This is the whole length here is 20, and you have here 20 cosine 60. So if you take the floor as reference, you will have the potential energy is mg times 20 minus 20 cosine 60. And what I want to tell you is that wherever you choose your reference, it will not affect your result, because at the end you care for delta y, and delta y will not change if you change the reference. Okay? So whatever the reference you take is, you will get the same result at the end. So now from the other side, we have the kinetic energy at B, which is half mvb square, and Vb is the only unknown in this equation, plus the gravitational potential at the final position. So for the final position here, if your reference was ceiling level, then you will have a negative potential. It will be minus mg times 20 cosine 15. So just instead of 60 degrees, you will replace by 15. And in case you take the floor as reference, it's a positive potential. It's plus weight times 20 minus 20 cosine 15. So here you can find the potential, general potential function of theta, and then at the initial state replace theta by 60, and at the final state replace theta by 50. Now, the only unknown in this equation is Vb, so I can calculate the value of Vb. Okay? Now, to continue, the other question was to determine the maximum value of the tension. In order to determine the maximum value of the tension, let us do the analysis. So we will do the analysis at any position theta, and then we can find function of theta. We can determine that as theta will decrease, the tension will increase, and we will see why. So first, if I consider any position here, the two forces acting on my particle are the weight and the tension. Okay? Now, since they are asking to find the tension, I need to use the Newton law. And because it's a circular motion, the best frame to work with here is UN UT. So UT is tangent to the path, and UN is along the radius directed towards the center of curvature. This is why here T is along UN. Okay? And since T is along UN, then to find T, I should write sum of N equals MAN. Now, to be able to project, I need also to know what is the angle between UN and the weight, because I need to project the weight. And since here this angle is theta, since this angle is theta, then the angle here also will be equal to theta. And now I can project the weight on UN by doing W cosine theta. Okay, and it's minus W cosine theta because it's a negative projection. So if I write the general equation along UN, I have plus T minus W cosine theta equals to mv square over the radius of curvature. Here the radius of curvature is the radius of the circle, which is equal to the length of the cable, which is 20. So over 20. Okay? Now, what can I deduce from this formula? As the velocity increase, the tension will increase. And the velocity will increase in which case? When I'm going downward. So we know that as I go down, so as theta is decreasing, the velocity is increasing. Okay? Plus, if I look here at my function, I have, if I take W cosine theta to the other side, then T is mv square over 20 plus W cosine theta. So higher is cosine theta, higher is T. And we know that as theta decreases, as cosine theta will increase. This is why we can conclude here that when theta is reduced, both cosine theta will increase and V will increase, and therefore T is increasing. So when theta decreases, T increases. And we can say that the maximum tension will be for minimum theta, and the maximum tension then will be for angle of 15 degrees. So now all I have to do is to replace in my formula. I got already the velocity when theta is equal to 15 degrees. It's 13.5. And I replace theta by 15 in the equation here. Then I can calculate the maximum value of my tension. Okay? Any question on this? Okay. So, can you give me 10 minutes of your time? Can we do this problem or? Okay, so let us do it. A smooth 2 kg collar C fits loosely on the vertical shaft. If the spring is unstretched when the collar is in position A, determine the speed at which the collar is moving when y is equal to 1 meter. If first A is released from rest at A, and in B if it's released at A with an upward velocity of 2 meters per second. So here we have a collar attached to a spring. The forces acting on the collar at any position will be the weight, W, the spring force, Fs. Now, we have a normal reaction between the collar and the rod, but this normal reaction is perpendicular to motion, so it cannot produce any work. Now, إذا بدكم to be very accurate, the normal will be in this direction. Why? Because look, the spring, as you can see, is developing. If you project on X, the spring force has a component towards the right. Okay, and you know that from this, from the constraint, the color cannot move in X, so sum of X should be 0. Okay, this is why when the spring is in tension, then it will push the collar in this way, and therefore the rod will develop a normal reaction to the right to have equilibrium in X. Okay, so N will be towards the left, and in this case, I don't care for the value of N because it will not do any work, so I don't need to calculate it. I have just the forces that are doing work are the weight, W, and the spring force, Fs, and both are conservative. So whenever all forces doing work are conservative, I can apply the principle of work, I can apply the principle of conservation of mechanical energy. The principle of work and energy is always applicable, okay? But the principle of conservation of mechanical energy is only applicable in case all forces doing work are conservative. So here, since this condition is satisfied, I can apply the conservation of mechanical energy. I have two types of potential energy here. I have the gravitational potential and I have the elastic potential. So I will consider then the mechanical energy conservation between position A and position C. Now, I need, for the gravitational potential, I need to consider a reference. I can consider that the initial position is the reference. This is why I can say that V gravitational at A is equal to 0. Now, for point C, I have C is below the datum, so V gravitational at C is equal to minus mg times 1. Now, concerning the elastic energy, they said that at the initial position, my spring is unstretched. So V elastic at A is equal to 0 because you know that the elastic potential is related to stretching or compression. So if it is unstretched, this means that the elastic potential is 0. Now at point C, in order to calculate V elastic at C, V elastic at C is half K delta L square. So I need to determine what is the stretching at point C. To determine the stretching at C, what is the definition of delta L? Delta L is the total length of the spring, so L at position C, minus L0. L0 is the unstretched length. It is the length at position A because at A it was unstretched, so L0 is 0.75. Now to get LC at this position, we need to get this length. So we can use Pythagorean theorem because look, you have here a right triangle. This distance is 1. This distance is 0.75. So you can calculate the length LC as radical of 1 square plus 0.75 square. And then now you can calculate delta L by saying that delta L is LC minus L0. So if you subtract 1, you will get the value of delta L at point C. And then you can calculate the potential elastic energy at C. Now, once I compute all of these, all I have to do is to replace in the conservation of mechanical energy. The only unknown in this equation will be the velocity at point C. Okay, because I know TA, VA, and VC, I can get then VC. Okay, now they just changed the question. Instead of starting from rest, if I push my collar with an upward velocity of 2 meters per second, okay, what will change? The only thing that will change in this equation is the kinetic energy at A. Instead of being 0, it will be half m times VA square. And according to this, I can calculate the corresponding new velocity at C. Now, just one remark. You have, if you push your collar up or down, and if you give it an upward velocity of plus 2 meters per second, or a downward velocity of minus 2 meters per second, the velocity at C will not change. Okay, why? What is the interpretation of this? The interpretation of this is that I don't have losses. So if I give it an upward velocity of 2 meters per second, when it will go back to C, it will reach C now with a downward velocity, but it will have the same magnitude of 2 meters per second because I have conservation of mechanical energy. So I don't have any losses. In case I have friction, it will be very different. In case I have friction, I will have losses and I cannot apply conservation of mechanical energy. Then the path will be important for me and I will apply the work and energy principle to find what is the final velocity at C. Okay? Any question on this? Thank you for your time and see you next time. And happy Easter. Bye bye.